on stage after 2 years. Welcome, welcome. Thank you all for having me. As mentioned, my name is Bobby Dorlus, and my friends actually call me Bobby D, so I hope you all call me Bobby D going forward. As mentioned, I am an ex-staff engineer at Twitter, and today we're going to be talking about solving efficiency challenges at data center scale. Quick introduction. I've been in the industry for about 20 years now. I started off about 2002 at the help desk, so I know what it feels like to be at the front desk, front door, to managing and supporting all the issues that everybody has, and eventually that has carried over my years in service because that's the type of design and systems that I do, is to ultimately reduce those type of toils and challenges we have at that level. As mentioned, I'm a founder of the Tech Hustle Twitter Space podcast, which is eventually going to be evolving into a tech company, really focusing on community outreach because I want to see more people that look like me in the audience like this, right? And ultimately taking technology, ultimately teaching technology to the level of engineering that I've experienced at Twitter. As mentioned, I'm ex-tweet. I'm at 9 years. I can't believe 9 years at a company. Wow. I'm a storyteller, motivational speaker. I'm a first-generation Haitian American. If you want to follow along, the barcode is there. Take a scan. And hashtag Team Dorlus is where you'll find me at. Today's conversation about solving efficiency challenges at data center scale. Now, a little sidebar. When I first started to develop this talk, it's so difficult to take a massive project like that and stream it down into an abstraction. So guess what? Today, I'm going to take this abstraction and make another abstraction. So we're going to abstract the abstraction because the concept that we have can definitely be a 3-hour talk, especially somebody like me that loves to talk. We're going to talk about SREing and what that means and how it's practiced at Twitter. We're also going to talk about the data center, the scale. 2 platforms we're going to focus on is the compute platform, which is a team that I worked on, and the storage platform, which gave me the opportunity to reach across the table as an engineer. This is principles and practices of staff engineering. Next, we're going to talk about capacity management. A little bit different than most in terms of just predicting, forecasting, and/or aligning it with a product delivery. I'm talking about capacity management by looking at what you have in your data center and finding inefficiency so that you can increase capacity and usage of those systems that you have. Next, we're going to talk about the technical implementation. This is the part that I can talk for hours about. We're going to look at a technology that's not new to the industry, especially if you're familiar with containerization, it's C group and namespace, and actually it's a little bit of past history experience working in Solaris that gave me the opportunity for me to build this type of implementation at scale. All right, so we're going to jump also into the 9-figure CAPEX savings. I know that number's extremely large, and I'm going to show the idea of finding the tip of an iceberg really turns out to be an iceberg because we saved 9 figures with this implementation. So before we get started, to get calibrated, how many people are familiar with SRE practices? Does SRE also? Awesome, awesome. How about infrastructure engineers? That's systems engineers, hardware engineers? Awesome, awesome. How about front-end software engineers? All right, back-end full stack. And then we got some directors, managers, and all that in between, yes? Few? All right. Thank you for helping me get calibrated. But what I wanted to do is just emphasize the practice of SREing. SREing for me really falls into the line of ensuring that the systems I build does not increase toil. Because as an SRE, if I'm dealing with toil, I am not having fun. How many people are familiar with toil? Toil, operational burden. I don't know, I feel like my voice got extremely high there. Operational burden. Operational burden, an example, working at the help desk, Monday morning, it didn't matter what day of the year it was, I picked up the phone and a customer's calling me, can you change my password? That takes me away from my desk, changing passwords, so on and so forth. We had to automate that out so that customers can fulfill those requests on their own. That's an example of toil and automating yourself out of a job, because that's another mantra that I live by. Another phrase and mantra that I always teach at Twitter about capacity is that I don't want to be paged as an SRE because we didn't plan for capacity. My firefighter suit and my boots are always next to my bed. When that pager duty alarm comes on, I'm ready to go. Imagine you get online and then you find out, man, it's because we didn't plan for capacity. Next time, don't wake me up, please. Please don't wake me up. But that's where we're going to focus on capacity in the sense of not just predicting capacity, but also taking advantage of capacity in-house, in your data centers, in your infrastructure, so that you don't have to purchase more capacity and or be at risk of not having capacity when you need it. Now, Site reliability engineer, this is a plug. I've recently featured in a blog post at Red Hat talking about site reliability engineer and systems architect. Definitely take a look. At the end of the slide, there will be a barcode again. It's all in my feed, and you can definitely find the slide decks included. But we're going to talk about data center scale first. Now, how many people run data centers on-premise? That's rack and stack, wiring, and all, right? Twitter, when I first explained to people about Twitter's infrastructure, one of the most things that catches them off guard is that we do run our own data center. Now, just think about Twitter scale, right? Running our own data center actually really requires us to do engineering a little bit different. This blog post here, which is something that's really cool about working at Twitter, is in terms of transparency, the company itself, and I actually mentioned 3, the company itself really leans on transparency, and this is a VP, an ex-VP, that wrote a very intensive blog post about our infrastructure and footprint so that you all can be mindful of just understanding the scale of Twitter. It's a real cool blog post. But when I think of what the data center looks like, when I explain it to students and mentees, I say it's a warehouse building, and we stack computers from the floor to the ceiling, and it's just rows and rows of computers. Now, the thing about Twitter being its own on-premise data center is that we don't run a lot of things out in the cloud. We are making some transitions and taking advantage of the resources out there, but running things on-premise has allowed us to do engineering to the next level. Not just looking at the surface, but getting down deep into the hardware and understand how computers really work. That's another skill set of mine. I didn't mention all of it, but my background is in systems engineering. I started off at the help desk, went up through systems administration into systems engineering, and eventually get an opportunity to do site reliability engineering. But you can't do site reliability engineering without writing code, so automating myself out of a job, infrastructure code, Python, and all that is definitely things that I'm well versed in. But at Twitter, working at our scale, one thing that we actually really have the luxury of doing is building our own computers. If you didn't know, Twitter has its own hardware engineering team. We don't buy from Dell, HP, or those companies. We actually build and manufacture them in-house, and then working with supply chain management for us to get hardware landing in our data center. Now, if you think about that whole process itself, you can really understand how in-depth we can get with changes in our infrastructure so that we can be as efficient as possible. Now, this diagram here is really just illustrating a default node. When I say default node, it's a computer. So we looked at a rack. We looked at a data center, we looked at racks, and inside of those racks has a computer. This is a default computer that the hardware engineer had been developing for a number of years, and really just came down to reducing differences in our data center. Because one thing that's an anti-pattern is when you have computers that are different. When you have this rack that's different from that rack, that means we have to increase toil and operational burden to manage that. So we went through a cycle a few years ago to actually really consolidate all of our platforms down to a unique data node, default node that's in terms of hardware, but unfortunately we had a side effect of that. And we're really going to find out what those inefficiencies were. The 4 components that come in computers: CPU, memory, disk, and network. Right? Remember those 4 components, and we'll see this slide further down the line. But we're going to get into capacity management. Anybody does capacity management, large scale, ordering hardware, yeah? Dealing with supply chain. I briefly mentioned and talk about capacity management in terms of being a challenge for us at Twitter, because if we're buying our own, or if we're building our own computers, we're manufacturing them overseas, and we have to have them shipped to our data center. Imagine what happened with COVID. All of that stopped, right? COVID came up, and guess what? We couldn't fulfill capacity demand like we normally do because it's 3 to 6 months pipeline for us to get supply into our data centers. That's why doing capacity management at this level, looking at what you have, also will reap the same benefits of adding new capacity to your data centers. And that's what we're going to get more into. When we think about capacity management, looking at a chart, looking at demand forecasts, looking at past experiences, looking at events. Twitter has gotten great at events. I don't know if you remember the farewell. I'm not going to throw it up there. We got rid of that thing. But during the time of events like Olympics, World Cups, or let's say the Oscars the other day, we predicted the capacity, but did we know the Oscars was going to pop off like that and there might be a spike? Those are opportunities where we design systems to manage that type of capacity at that scale. And this is where I say, don't page me because we didn't plan for capacity, because I know we have it in there, right? But what does the data center footprint look like? if you look inside of our data center, and this is actually a chart coming from the blog post that I mentioned earlier, is that we service two main type of workloads. You're either running on compute, which is the team I work on, or you run on our storage platforms. I put an S in there because we offer a few different types of storage platforms. But the compute side of the house is something I can talk hours about. And we'll talk a little bit about what platform we use in terms of compute, but just be mindful, the infrastructure itself that we're talking about is hyperscale. We're not talking about 100 computers, 1,000 computers. We're talking about tens of thousands to close to hundreds of thousands of computers in one building, separated into some type of zone, power distribution, and things like that, but that's the scale that Twitter works at, and that's the compute platform. And then the storage platform on the other side is also world-class. We run one of the world's largest Hadoop clusters, right? We run a very low latency key value store, blob store. Every image that you upload to Twitter goes into this type of system called the storage platforms. But let's first take a look at the compute platform. This is a very stripped-down architectural diagram, and the thing that I just want everybody to be noteful of is, number one, we are running Aurora Mesos. Anybody ran Aurora Mesos before? Raise your hand. Yeah. I know every time I mention Aurora Mesos, somebody says something about Kubernetes. I know it's coming, but it's all right. The thing that I want to mention about scale-wise, the problem that we're trying to solve with running systems at scale is being able to manage hundreds of thousands of containers. I've been talking about hardware scale. Now I'm talking about a little bit higher in the container scale. We run hundreds of thousands of containers in one of our clusters, and those are the type of requirements that we have for the next platform we're going to iterate to, and I'll talk some more about that in terms of Kubernetes. But the thing that I want to talk about in terms of how we're using this default node and the compute platform, the things that mostly we are focusing on when we're reviewing and analyzing the uses of our systems is those 4 key points that I mentioned earlier. CPU, memory, network, and disk. Now, I ordered these in terms of the priority that the compute platform uses each of those resources. CPUs, we'll take as many CPUs as they have, and we'll take even more, right? We run millions of CPUs and millions of cores in one of our clusters, and we can only grow even farther and more or less double that footprint if we needed to. But in terms of the actual resources that the compute platform relies on the most, it's the top 3 listed there: CPU, memory, and network. Disk for us, we don't persist disk at all. If you run workload on this platform here, we tell you 2 things. Number 1, bring your own dependencies because we ain't got nothing for you. And then the second thing we say is don't store anything in your sandbox because before you leave, it's going to be gone. And with those type of implementation is actually give our customers a way for them to design systems so that they don't rely on the compute platform to store persistent data. But where do they go and put that data, right? We tell them if you need to store persistent data, go talk to a storage platform provider, and they will actually be able to have a system perform any type of algorithm replication factor that you need to support your use case, and that's how we're able to grow our compute platform as large as it is because we don't store any type of persistent data. But we're going to move on to the storage platform. These are the names of our storage platforms, and more specifically, we're going to be looking at Manhattan and Blob Store. Manhattan's our key value store, and Blob Store is our blob image, so any videos or media that you upload to Twitter gets replicated in this infrastructure. We're going to take a very stripped-down architecture diagram and look at the storage platform, which has some type of coordinator, metadata. Data's written to disk on some worker nodes, right? And then as a user, you're requesting data, and then the metadata tells you where to go get it, and then we send it across the wire as fast as possible, so on and so forth. But what are the use case for the default platform for storage nodes? Their top list is disk. Obviously, they're maintaining persistent data, right? Memory, right? We have caching infrastructure that sits in front of some of our storage infrastructure, but they're caching infrastructure themselves, so they're using memory. Then their third most used resource is network. We got to replicate bits across the internet, not a little bit across the internet, but replicate bits inside the data center across different data centers. But in general, those are the top 3 resources. If you notice, CPU is at the bottom. And this is where the analysis that we had really came into light because we found out that our storage platforms were using less than 20% of the CPU resources inside of those machines. So as a staff engineer and staff in terms of platform staff, empowering us to go and say, go look at ways to become better at these inefficiencies, I decided to have a conversation with storage. when I pulled up to them, they said, yo, we running everything good. But I was telling them they have an engine bigger than the car they're driving. Truly. And the idea here is that we fully understood that the CPUs that we provided them are our standard CPUs. We knew that's inside of our data center, but they were not able to use them to the full potential. Storage systems have some limitations in terms of sockets compared to disk, and or just the design of those storage systems from the ground up really doesn't take advantage of the new hardware infrastructure that we have available. But the conversation really came down to, is there any way, as a staff engineer, that I could take my technical influence and help this organization to take advantage of resources that are underutilized? This is the nugget here, because once I found this, it wasn't in one computer. It wasn't in 10. It wasn't in 100. It was not 1,000. It was tens of thousands of computers look just like this, right? So next, we're going to talk about the technical implementation to ultimately, ideally, if we keep this up, is like having this engine with 2 cars under it, because we're going to run 2 different type of workloads on this box and this computer here. So if we look at the technical implementation, if the slide will go next, there we go. We're going to talk about the technical implementation for us to get 2 cars under that one engine. Before I get started, I briefly mentioned about Solaris 10, so I want to tell you a story. And this right here is where, as staff engineers and above, our years of experience can help influence the organizations that we work at now, right? 10 years ago, I worked for a company called, I worked for the state of Florida at the South Florida Water Management District. This is an organization that managed the water flow in terms of rain and water that's in the Everglades, in the lake, right? If it overflows, we open some gates. If it's not enough, we'll close the gates. But that infrastructure, or that system that we worked on, really gave me an opportunity to be exposed to containerization 10 years ago, because with Solaris 10, anybody ran Solaris 10? Raise your hand. We got 1, 2, 3, a few. Awesome. Solaris 10 introduced a technology called zones, which is the same thing as containerization in the Linux kernel. They were just a few years early, right? And because I had exposure working with containerization with Solaris and zones, that same implementation is what I implemented here at Twitter. Now, this is where you make that connection in terms of your years of experience as engineers in our industry, is that the knowledge you gain at past companies or experiences is the true asset that you're taking with you when you go to another organization, right? Now, think about C group isolation, namespace. There may be terms that you're not familiar with, but if you scrap away Mesos and Aurora, you scrap away Docker containers, you scrap away Kubernetes, and you get down to the foundational Linux kernel features that allows us to create the isolation, these are those 2 features called C groups and namespace. I can talk for hours about these, because this actually has been the foundation for our compute cluster for us to be able to run those hundreds of thousands of containers. Now, we're back at the default node, right? And the thing, as a systems engineer like myself, sometimes when you're actually involved in designing systems like this, you really get a chance to showcase some of your past experience, because this right here, creating this barrier on the default node, is truly the baseline of the implementation for us to run 2 different type of workloads on the same bare metal machine. Now, before I even continue, there were some things that we did consider. Virtualization at the hypervisor level, right? We could have ran VMs with any of the hypervisor softwares that are available, but remember, anti-patterns for us is differences in our environment. We would have to run virtual machines only on these platforms, and increasing that type of differences is increasing toil and operational burden in the long run, so we couldn't go down that direction. We actually consider an option of disabling one of the sockets. I was speaking to one of the speakers last night, is that we could have said 1 socket is turned off and only 1 runs. Now, who goes buy 2 and only use 1, right? Like, that's a waste, right? So this introduction of C groups and namespace was that next level up for us to not increase operational burden and toil, because we're going to automate ourselves out of our job, but take advantage of new kernel features that allow us to create this isolation here, so that when storage workloads runs on this machine, we tell storage, like, yo, only run on socket 0, because socket 0 has the 3 things that you need the most, which is disk, memory, and network. And then we said, for compute workload, which fit perfectly on the other side of the socket, which also has similar obsessions, but focused on CPU, memory, and network, could run on the other socket. Eureka, this is it. This is the implementation that when we went and talked to our manufacturers, remember, we're buying computers overseas or wherever our manufacturers are, we went there and said, yo, last week we wanted 2, this week we only want 1 computer, right? Now imagine how that compounds into our infrastructure, because remember, we're at scale. We buy 10,000 computers, now we only need 5,000, right? That right there is where we're gonna start to really dive into how did we get to 9 figures in CAPEX savings. Now, when I originally proposed this talk, I wanted to give you all the formulas, I wanted to give you all the data, but you know Twitter. Like, why? How are you gonna talk about 9 figures and put our business out like that? So I'm gonna keep it simple and keep it straight to the point. Just think about scale. Every time we introduce this platform, this default platform that we created called colocation, we were saving half of that node off rip, because we were able to run 2 different types of workloads without increasing capacity. In terms of, I didn't have to buy a new server because I looked inside of our data center and we leveled up this whole rack, right? It used to be only storage that ran in this rack. Now this rack and rows run storage and compute, right? And just imagine those amount of resources that we had sitting there waiting for when that next event happened. So when Oscars happened, because this has been running in production for almost a year and a half, those workloads were just right there ready to expand and grow into a whole rack of nodes that before we would not even have been able to consider inside of our compute cluster. And then another side effect, which we can go into more details about, find me afterwards and I can enlighten you on this, is our storage platforms' tail latencies actually got way better. And the result of that is because they were pinned to a specific core, they didn't have to go across this highway called a QPI, and guess what? Their service works way better. And you know what? The default configuration for storage platforms going forward was in this colocation mode. Now, how do we get to 9 figures? Just take this data center and end that data center. We have multiple data centers that look just like this, right? I'm not gonna give you exact numbers, but we have multiple rows that have those type of systems in that configuration. Multiply that. And also think about the cost savings when we have to go talk to our manufacturers. We're negotiating new kind of deals. That compounding effect not only took place inside the data center that we have, but it's also the same thing that happened for all of our new data centers. So that when we look at that pie chart, yes, storage and compute is still a very large footprint, but we found 10%, close to 10% of resources that were underutilized that we could easily add into our cluster. This all happened right before COVID. This all happened right before we didn't have access to anything in terms of finding resources for us to increase the workload. So projects like this, and we'll have some more takeaways at the end, really gives us an insightful view on what we can achieve in terms of looking inside of your data center in terms of capacity management, and ultimately find yourself finding resources that are sitting there doing nothing. And no new toil, right? For me, it was like a match made in heaven, truly, because the infrastructure that we created, the change that we introduced, tens of thousands of nodes in data center, was all automated. With one flip of a bit, we can have a node be a storage node, and flip it back, now it's a colocation node, and we can work and have more type of workloads landing on that machine. Now, in conclusion, one thing that this type of effort really gives me insightful views on is that technology is always iterating. And sometimes we may be re-implementing technology that's already been around for a while. Make sure you just look in your tool bags. The new shiny toy looks like a new shiny toy, right? But the old toy that you played with for so many years is very reliable, very consistent, and you are very aware of what you can achieve with that type of technology. So solving inefficiency challenges at data center scale truly is what resulted in this project, because we saved Twitter that 9-figure. When I tell students on this, talk to students and mentees about this project, I really label it as, hey, I'm saving the planet because we didn't have to build a new data center, right? That's the type of scale that this type of implementation can take, because I truly feel like the infrastructure that I support is as large as the pyramids in Giza. Like everybody, how many people use Twitter? Raise your hand if you use Twitter, right? And raise your hand if you even know Twitter. If you've seen the bird, would you know, right? I'm telling you, everybody in this room knows Twitter, so that infrastructure is massive, and solving these problems at data center scale truly has a long-term effect, and I've been so, how can I say, taken back about my experience over the years to give me an opportunity to work at this scale. Now, before we close it out, I know Kubernetes was mentioned in the abstract. I know I didn't even mention Kubernetes not one time, and big shout outs to Kubernetes and what it's gonna create. I will say, Kubernetes has big shoes to fill when it comes to running at Twitter scale. It truly does. There are some limitations. It's iterative. Eventually it'll be there. But compared to Mesos and Aurora, we've been running it for 8 years at Twitter, and it was built at Twitter initially. So the reason why I put Kubernetes in the slide is Twitter's hiring. If you're looking for an opportunity to work on Kubernetes at a massive hyperscale, holla at Twitter. Another thing, if you're looking for opportunities to be yourself, because me on stage like this, imagine an engineer that looks like me feeling confident enough to speak on a technical level like this and be on stage, and it's because I had the experience of being a tweep, truly. Twitter's hiring. I could not have done this all by myself. Truly, gratitude comes to my peer group and other staff engineers that I've worked with. It was a real small group of engineers that accomplished this task. I'll say it's about 5 of us on hand. And in general, the cost savings was massive that management was like, yo, you 5 just go and do whatever you want because the analysis shows that we will be able to get to this result. Now, the thing that I want you all to take away from this talk, and I've mentioned it multiple times, is that the tip of the iceberg, the tip may be what you see, but once you see what's below the waterline, once you see how this simple implementation, I say simple because I'm re-implementing it again from experience with Solaris and now in Linux, we were able to save 9 figures. That iceberg goes way deep. And just know that your skill set as staff engineers, your asset, your true asset is the knowledge that you have, and management and everybody in your organization is looking for you to give them guidance. Give them, because I have had the opportunity to work with a lot of newer engineers in this industry, and when I talk about bare metal, they're like, yo, where's the VM at? And I'm like, no, we're talking about this computer here, and they just don't make that connection, right? Our industry is constantly iterating and abstracting away hardware. Most people don't even know about hardware, and that's what it's meant to be because we want to make sure that when hardware fails, you don't even know it failed, creating those hidden mirrors. So keep that in mind as you continue to iterate on your journey. I really appreciate your time. There goes my barcode again. I will be walking around, being available for more conversations, and definitely look forward to connecting with everyone. Thank you for allowing me to be a part of your group. Holla at your boys, Bobby B.
Great.